Hi everyone, welcome to this video lecture on the DDPG algorithm. The purpose of this video is to help you develop an intuition for the DDPG algorithm so that you can understand it on a deeper level. When I first tried to understand this algorithm, I was never able to understand the notion of the actor and critic networks. Why are there two separate critics and two separate actors? How do get things get done in between them? And what is the need of each of these network? Then these scary looking equations and everything. So the whole concept of DDPG algorithm was quite confusing for me in my mind, and I had to spend a lot of time digging into multiple articles and watching multiple videos to truly understand it. But in this video, I'm going to share my intuition with you guys so that you guys might not have to spend equal amount of time for it. So yeah, let's just jump into it. Now let's move into the algorithm itself. Before I start with the algorithm, I want to tell you that this is the first time I'm putting an instructional video on YouTube, so bear with me. So before we start with the DDPG algorithm, which stands for Deep Deterministic Policy Gradient, we have to understand what is the promise of DDPG algorithm. The DDPG algorithm says that if you are going to give me a state S, I am going to give you the best action A that you can take from this given state. So the promise of the DDPG algorithm is that if you are going to give me a state, I'm going to predict the best action A that you can take from this state S. Now the promise of the DDPG algorithm is clear to us. Now let's move to the next thing, that what is going to be the data for our algorithm. So the data is going to be the experiences of our agent. The agent is going to take an action A in the environment. The environment is going to reward it with reward R, and the agent is going to move into a new state S dash. It should be S dash here. So after playing the game, after moving into the environment for hundreds or thousands or millions of the time, we would have a lot of experiences, a lot of movements, and we store all of these movements into a data structure that we call the replay buffer. Each movement is represented by this tuple, which is SAR S dash. S represents the current state, A represents the action it took, and R represents the reward it got. And S dash represents the state it got after it took the action A. So this is the data of our algorithm. So now we know the promise of the DDPG algorithm and the data it is going to use for its training. Now let's move into the components of the DDPG algorithm. So the DDPG algorithm makes use of two neural networks, namely the critic network and the actor network. The promise of the critic network is that if you are going to give it a state and the action it took from that state, it is going to give you the Q value of that state action pair. The promise of the critic network is that if you are going to give me a state and the action you took from that state, I am going to predict the Q value for that state action pair. What is the Q value? Q value is basically an estimate of how good that action was in that state S. So remember the inputs S and A, that is, if we have a state and action and we want to predict the Q value for that state action pair, we can use a critic network. Same goes for the actor network. The promise for the actor network is that if you are going to give me a state, I'm going to predict the best action that you can take from that state S. So the input is state and the output is A, an action. So I want you to really think about these inputs and outputs and remember them. The input to a critic network is a state and action, and the output is the Q value of that state action pair. The input to an actor network is the state, and the output is the best action A from that state S. Please remember these input output pairs because you are going to use them in the next in the actual algorithm itself. You would know that what is the input and output of a critic network and an actor network. So now let's move to the actual DDPG algorithm itself. So now we know that what is going to be the training data for our algorithm and what is the promise of the DDPG algorithm. And we also know that the components of the DDPG algorithm, which is a critic network and an actor network. Now let's understand how the DDPG algorithm works internally using this critic and actor network. So now we know that we have two networks. We have a critic network and an actor network. Both of them are neural networks. So we would need to train them because neural networks are only going to make good predictions if they are properly trained, or I should say sufficiently trained. So let's start with the training of the critic. How the critic is trained. What is the basic promise of the critic network? The critic network says that if you are going to provide me a state S and an action A, I'm going to predict the Q value for this state action pair S and A. So the input of a critic network is S and A and output of Q of SA. In a neural network, we know that the network is going to make a prediction and we are going to compare this prediction against another value. Then we are going to take For example, the subtraction of it, the basically we are going to subtract the two values and we are going to get a value which is called loss, and the network is going to strive to minimize that loss. So if this network makes a prediction, the prediction of it is going to be compared against some value, the subtraction of them is going to be taken, and then the network is going to strive to minimize that value, that is the loss. So now we have the prediction of this network, critic network, that what is going to be the output of this critic network. The output of this critic network is going to be the q value for the state action pair. Let me open paint. So yeah, the output of this critic is going to be some value. Let's represent it by q of s of a. I do not have a pen, I'm using a mouse, so pardon me. ah. So it is going to predict s of q of s of a. It needs to be compared against some value, let's call it y, so that the difference in between them can be calculated. The difference is called loss, and then we are going to strive to minimize that loss. So now we have to think that what is going to serve as y? What should y be so that we can train our network? Remember that this here is the q value of a state action pair. So one thing is understood, that y is also going to be some q value for the given state action pair. But what q value it is going to be? So now let's understand the notion or intuition of optimality. We know that this DDPG algorithm is an off-policy algorithm. And what is the notion in an off-policy algorithm? In an off-policy algorithm, we are always striving for optimality. We are always striving to take the best action from any given state S. So the vibe of an off-policy algorithm is optimality. We are trying to achieve optimality. So DDPG is also an off-policy algorithm, which means that everything in this algorithm should reach optimality. So I can say that this value y, I already know that is going to be a q value. That is a certain, because we cannot compare a q value against something other than q value. So I know that the value of y, this y is going to be a q value. But what q value it is going to be? Because we are running an off-policy algorithm, this y is going to represent the q value for this state action pair in the most optimal conditions. Let me explain it more. This the q value of a state action pair under multiple conditions can be different. For example, if the policy is not good, very good, it can have a q value of 5. If the policy is better than the previous one, it can have a value of 7. Or if the policy is the most optimal, it can have a value of 10. Is the value 5 in the most optimal conditions? No. Is the value 10 in the most optimal condition? No. Both of them are still q values of the state action pair under some conditions, under some policy, but they are not under the most optimal policy. Is 10 the q value of the state action pair? Yes, it is the q value of the state action pair in the most optimal conditions. And because we are using an off policy algorithm, this y should represent the most optimal condition, the most optimal value for the state action pair. Because we are training this network, if we are going to put the most optimal value of y, the network is going to strive to reach the most optimal value for the state action pair. Understood? The if we are going to if we are not striving to be optimal, then it can also reach 5, it can also reach 7, but because we are making it strive to be as optimal as possible, we are going to make this y 10. So the network is going to start from some value, some q value for this state action pair, maybe 3, maybe 1, or anything, but it is going to strive to reach 10. So this is how the critic network is trained. Now there is a problem. What is the problem? The data we get to train this algorithm, which is represented by this replay buffer, does not have y. It does not have the q value for the state action pair under the most optimal conditions. So does that means that we pack our bags and go home? No. Think about it. Even in our daily life, when we do not have the exact value of a thing, what we try to do? We try to estimate it. We try to calculate it from what we already know about that. particular thing. So for example, if you are trying to estimate the net worth of a person and you do not know the exact figure, what you are going to do is that you are going to try to estimate the net worth of that person from the kind of house that person is living or the kind of clothes that person is wearing. So you can get a very close estimate of that person's net worth from the factors that you already know about it. We are going to apply the same concept here. What we can do to find the Q value of a given state action pair, we can use a Bellman equation, because if we use the Bellman equation, we can estimate the Q value for this state action pair. So this here represents the Bellman equation for this state action pair. Remember what is y? Y represents the Q value of the state action pair in the most optimal condition, because we are following off policy. Now, in order to calculate y, what are we going to need? According to the Bellman equation, we are going to need the reward it got. Do we have the reward for this state action? Yes, in the replay buffer, we do get the reward that we got from the state action pair. Then we need this something called gamma. Gamma, we already know that gamma is something that we decide ourselves. We do not need to get it from the environment. We decide gamma on our own. We try with gamma. It is sort of like a hyperparameter that we change within our network. This is basically a value that we can ascertain ourselves. We can use any value for it. We do not need it from the environment. Then there is this part, which is q dash of s dash a dash. This part here represents the q value of the next state action pair. Do we have the q value for the next state action pair in the data we receive? No, we do not have the q value for the next state action pair. So what do we do when we do not know a particular we do not know the value of a particular variable? We try to estimate it from what we already know. So now we have to think, is there any algorithm or anything I have that if we give it a state and an action, it is going to predict the q value for it? Think about it. Yes, we have. We learned that if I have a state and action pair and I want to predict the q value of it, I can use a critic network. So I have a problem where I need to find the q value of a given state action pair. This critic network does exactly that. So I am going to introduce a new critic network into my algorithm, whose whole responsibility is to predict this particular s dash a dash pair's q value. So this is from where the critic network comes, the target critic network comes. This is the actual critic network that we are trying to train. And in order to train this online critic network, we encounter a situation where we needed to estimate the q value of the next state action pair. So in order to predict this next state action pair, we introduce another critic network, because the promise of a critic network is that if you are going to provide it a state and an action, it is going to give you the q value for it. But is the problem solved or not? We have R, we have gamma, but inside this Q value, there are two symbols. There is S dash and A dash. Do we have the S dash? S dash is basically the next state that we are going to be in after taking action A in state S. Do we get it? Yes. In the replay buffer, we do get S dash. So S dash is sorted. But do we have A dash? What is A dash? A dash is basically the action that the agent took after when it was in the state s dash. Do we have a dash in our replay buffer? That is the data we receive to train our algorithm? No. So that means that, like all the other things, we need to estimate a dash from something that we already know. So now think, I have a state and I need to predict the best action that I can take from this state. Why I said the best action? Because we are training off policy. We are trying to achieve optimality. We are trying to do everything the best possible way. So I'm going to take not any action but the best action from here, from this state s dash. So think about it. We have a state and we need to predict an action. Do we have any algorithm or anything that we can use to predict and the best action given the state? Yes, we studied that. An actor network is a network that if we give it a state S, it is going to predict the best action A that we can take from this state S. So the problem is solved. For estimating the best action, we are going to plug our target actor network as well in our algorithm. So we plugged the critic network to predict this Q dash term, and we plugged the target actor network to predict this A dash term. So this is where these both target networks come into play. These target networks basically help us to train the actual critic and actor network. So let's summarize a bit what we have understood so far. We had the replay buffer which gave us SAR and S dash. We need it to train the critic network. The critic network predicts a Q value. The Q value needs to be compared against another Q value so that the loss can be estimated. That target Q value Y, we represent that target Q value with Y is going to be the Q value for the state action pair under the most optimal conditions because we are following an off policy. So now we know that we need to estimate this y value which represents the q value under the most optimal conditions, but we do not have everything that is needed to estimate it. So we find out what we already know and we don't know. So for the things that we don't know, we make help of. So yeah, we in order to estimate the things that we don't know, we make use of the knowledge that we already have to estimate them. So we did not know Q dash beforehand, so we are going to take help from the target critic network to estimate Q dash, and inside Q dash we have A dash which we do not know. So in order to estimate A dash, we are going to take help from the target actor network. So this portion of the whole DDPG algorithm is understood. Once the online critic network is going to make a prediction, and it is going to be compared against this value y, we are going to calculate the loss, and then this critic network is going to strive to minimize this loss. So for example, during the let's take we were in state S and we take action right, and the q value we got was 5, but the optimal value is 10. So the next time for the same example, uh, we are going to improve. This is an important concept here as well, that the y value is not going to remain the same throughout the network, because as the weight of these network are going to change. Sorry guys, there is some disturbance on my part. So I was saying that when again the network is going to reach the same example, y is not going to be the same. Why is y not going to be the same? Because this y depends upon the predictions of these two neural networks, the target actor and the target critic, and these two neural networks are going to change with the passage of time in order to improve their predictions. So the next time y might be 11, but with the passage of the time, the predictions of this online critic network are going to be get better and better and nearer to this y value, to these y values. So by the end of millions of example, our online critic is going to be trained, and the prediction it is going to make are going to be near the true y values. Okay, now we have understood this side of the puzzle, which is the critic network. I know that sometimes I might not have been able to make it click or confuse you. Do not worry, in the end, I'm going to make sense of it all. I promise you. So now let's move towards the actor network. Now remember what is the promise of the actor network. The actor network says that if you are going to give me a state S, I am going to give you the best action A that you can take from that state S. This is the promise of an actor network. So now we need to train this actor network. So what we are going to do is that we are going to take the state S from the replay buffer and we are going to pass it to the actor network. Now the actor network once receives a state S, it is going to make a prediction of an action A, which is represented here. Now we had a state S and the actor network make a prediction of action A for it. Now there should be some mechanism to compare its prediction against something so that it can create better and better predictions for the given state. So we have a state and we have the corresponding action that the actor gave it for us. What can we do for a state action pair to know that whether it was good or not? We can estimate the Q value of it. Yes. What basically does a Q value tell us? A Q value basically tell us that in the given state S, when you took the action A, how good was it? And this exactly we need here. We need to estimate, we need to calculate that the action that the actor gave us, whether it was good or not. So we need to estimate the Q value of the given state action pair. Is there anything in my algorithm that can help us estimate the Q value given a state action? Yes, we have just trained an online critic which given a state action pair is going to give us the Q value for it. So in order to train the actor, what we are going to do is that we are going to pass the state into the actor. The actor is going to give us an action corresponding to the past state. Now that we have the state action pair, we are going to make use of the online critic network to estimate the Q value of it. The online critic network is going to give us the estimated Q value, and we are going to pass it metaphorically pass it to the actor to make a better action next time, to predict a better action next time, so that the corresponding Q value would be greater than before. For example, we pass the state S into the actor, it created an action A, and for that corresponding state action pair, let's call it A1, we got a reward of 5. The next time we are going to pass the same state S into the actor network, it is going to predict a new action A2, which is going to give us a Q value of 7. So with the passage of time, the actor is going to get better and better in maximizing this Q value. So by the end, what the actor would be great at is that it is going to make a prediction of an action. It is going to give us the action which maximizes our Q value given this state S. You can see the state remains the same, only the action changes. What we are trying to solve is that we need the action from the actor that will eventually give us the maximum Q value here. So we can say that for given state S, we need A optimal from the actor. I'm representing optimal with this O. So when we have this state A and this action A optimal, we will have the max Q value for this given state action pair. So this is basically the purpose of the actor network. So now we know that for what purpose the critic is used. We know that for what purpose the actor is used. Critic is trained to estimate the Q value of a given state action pair, and the actor is trained to give us the best action given the state. Does something click here? What is the promise of the DDPG algorithm? The promise of the DDPG algorithm is that if you are going to pass a state S into me, I'm going to the best action A that you can take from this state S. Isn't it the same thing that this actor S is doing? After training, it is going to give you the best action A that you can take from the state S. This is, my friends, how the DDPG algorithm works. Now we have this actor A, sorry, we now have this actor which can predict the best action given any state S. We can virtually throw away all these online critic, target actor, target critic, and we can just, for any given state that is passed into our algorithm, we can make the estimation of the best action using our online actor, and we can pass it back to the agent, which is basically the promise of the DDPG algorithm. This is, my friends, how the DDPG algorithm works. This is basically the intuition of the DDPG algorithm. Uh, if you have any confusion, I know that I might not been able to make some points clear. Please ask them in the comment section. I do not care if you like or share the video, but if you had a question in your mind and you did not ask, it is going to be an insult to my effort, because I am trying to become a better and better teacher, and it is only your criticism, the constructive criticism, that is going to make me a better teacher. So if you have understood the algorithm, congratulations. The same underlying principle is used for SAC, which is soft actor critic, and the other one is the twin delayed DPG, DDPG. The same principle is used behind those two as well. So with this mental model in mind, you can learn both of these algorithms as well. If you want to find some reading material for it, then I would recommend the Open AI Spinning Up docs. Here you can find all of these algorithms, the Deep Deterministic Policy Gradient, the Twin Delay DDPG, the Soft Vector Critic method. Then you have the policy gradient methods like TRPO and PPO. Everything you can read from here. Now that you have understood the intuition behind DDPG, you can understand the DDPG algorithm itself. It is a little different than uh, what I have taught you in the video, but basically the mental model is the same. You can also understand that twin delayed DDPG and the soft factor critic method, the same mental model is going to work for them. The mental model for these three is going to be a little different, and I'm going to try to make a video for these three as well. But I've tried my best to make you understand the intuition behind DDPG, and I hope that I was successful. Please share all your questions and comments in the comment section, and I will see you in the next video. Thank you.